Okay, what we're going to move on to in this lecture is looking at what has to happen with calculus in order to be able to apply it in the case that the functions we are dealing with have complex valued range. So the first part, I'm going to look at the subject of differential calculus as it applies to complex numbers. So I'm going to start off by giving a quick look at why calculus with respect to complex numbers could potentially raise difficulties if we're not careful. So these difficulties arise from the fact that a complex number consists of two separate objects, the real part and the imaginary part. And that behavior, that raises a number of technical difficulties when we try and extend classical calculus, particularly integral calculus as it turns out, to the complex arena. Okay, so these problems, particularly in integral calculus, these are arising from the fact that the complex numbers cannot be ordered, the fact that we cannot give a sensible meaning to the phrase, this complex number is smaller than some other complex number. So the class of functions we are looking at are where the input value is a complex number and the output value is a complex number. So we're mapping from complex numbers to complex numbers. What if we're mapping from real numbers to complex numbers? Well, it turns out that that particular case is actually fairly easy to handle because all we are dealing with in this particular instance are two real valued functions. The function that is defined as the real part, which maps from real numbers to real numbers, and similarly the function is defined for the imaginary part. That also maps from real numbers to real numbers. So what that means is we take our function, which is mapping from real values to complex values, and we can write that as a function defining the real part plus this object I multiplied by the function defining the imaginary part. And if we look at our standard calculus rules that we saw a few lectures ago, the first derivative that we find is the first derivative of the real part function plus I multiplied by the first derivative of the imaginary part function. And we get a similar simplification when it comes to integration. The fact that complex numbers are not ordered doesn't arise because we're dealing with a domain over the real numbers. So P and Q here are both real numbers. We can think of one being smaller than the other. So in the same way as we had with differential calculus, we can treat the problem of integration as merely involving two separate structures added together to define the integral form. When we turn to looking at functions whose domain is a complex number and whose range is a complex number, well, things become more interesting. We have to take a lot more care. So what I'm going to look at in this lecture are the particular considerations we need for differential calculus. So let's turn back to our typical complex number, this object formed by adding a real number to I multiplied by another real number, our standard form. So one way we can think of such functions are as consisting of two real valued functions. So our typical complex valued function we can rewrite in this form, and we can expand that to involve our two real valued functions u and v when we write it in this form here. So what we have is a function of two real variables which produces as a result two real valued functions, each of those being functions of two real variables. So what that's suggesting as our mechanism for extending differential calculus is that we look at partial derivatives. Now, in order for the first derivative of a complex valued function to be defined in a sensible way via partial derivatives, we need two important preconditions to be satisfied. And these are what are known as the Cauchy-Riemann conditions. And they state, if we look at the partial derivative of u with respect to p, that is exactly the same function as the partial derivative of v with respect to q. So that's the first of the Cauchy-Riemann conditions. The second condition is that the partial derivative of u with respect to q is exactly the same as the negation of the partial derivative of v with respect to p. So I stress again, these are conditions on functions, on the functions u and v, defining the real and imaginary parts of the output. Now, you might be wondering, why do things have to be so complicated? Why is this so involved? Well, let's turn back to our original development of this idea of what we mean by the first derivative of a function, the real valued case. So when we did that, this was defined as an object that resulted by studying the behavior of this ratio as some value approaches zero. And we could try taking the same approach with complex valued functions. And when we do that, we run into a problem, because if this value h is a complex number and we're looking at how it approaches zero, then we have to consider how the real part approaches zero and how the imaginary part approaches zero. Now, in our original case with real values, we really only have one direction in which this can be defined. It could be a negative number becoming larger or a positive number becoming smaller. But effectively, we only have one way in which our value can approach zero in the real case. In the complex case, we can have infinitely many different ways of the term approaching zero. And so that raises a problem if we're trying to produce a notion of first derivative through this idea of studying limits. Very informally, what the Cauchy-Riemann conditions are saying is that it doesn't matter that there are infinitely many different ways of a limit approaching zero, because these are all equivalent. We can treat them in exactly the same way. So here's an example. Suppose we go back to our function of squaring a complex number, this basic function here. Then if we take our arbitrary complex number form, what we have the function defining the real part of the output, that is given by the real part of this expression, which we've seen earlier is p squared minus q squared. The real part squared minus the imaginary part squared. If we look at the corresponding imaginary part function, the imaginary part of this expression, this is 2 multiplied by the real part multiplied by the imaginary part. So there are our defining two real valued functions of two variables that we need to capture the operation of squaring a complex number. And if we look at the partial derivatives, what do we see? The partial derivative of this function with respect to p, that's 2 multiplied by p, this term disappears, so we get the partial derivative in this case is that function. If we look at the partial derivative of this function, but this time with respect to q, we get 2 multiplied by p as well. So the first of our Cauchy-Riemann conditions is satisfied. The second of our Cauchy-Riemann conditions is also satisfied. If we look at the partial derivative of this function with respect to q, then this term disappears and we get 2 multiplied by minus q, this term here. If we look at the partial derivative of this function with respect to p, once again we get 2 times q, and we're looking at a negation condition here. So again, the second of the Cauchy-Riemann conditions is satisfied. Now, if we were to try applying our standard approach to differentiation with this function, then the outcome would be 2 multiplied by z. And if we expand what's happening here, we see that is exactly the outcome we would get from partial differentiation. So the Cauchy-Riemann conditions, in effect, what they've established is that this rule for differentiating powers, this is valid in the case of complex numbers in exactly the same way that it's valid for real numbers. Here's another example. Suppose we look at the complex conjugate function. Here we have the expansion of our complex conjugate function in terms of our standard representation for complex numbers is given by this. So the real part of the function, the real function is this, just the real value p, and the imaginary part is just the function given by the negation of the q. These two functions do not satisfy the Cauchy-Riemann conditions. To see that, we look at the partial derivative of this function with respect to p, the outcome of 1. But the partial derivative of this function with respect to q, that's minus 1. So these two are not equal. So what we see from that is that the complex conjugate function cannot be differentiated. It's not differentiable. Here's another, again, a rather more complicated example. Suppose we look at the function defined by 1 divided by some complex number. So to start off with, we rewrite it. We saw earlier how the operation of complex division is defined. It's a complex conjugate divided by the size of the complex number squared. This expression here. So we go back, we write our standard form for the complex number, this structure here, and if we carry out the analysis, what we find from this definition is this is corresponding to the function given by complex conjugate divided by the size of the complex number squared, and in this case we have this form for the real part and this form for the imaginary part functions. And I'm going to be lazy, I'm going to leave you to confirm that these two functions satisfy the Cauchy-Riemann conditions and to derive the expression for the corresponding derivative of that function. Okay, so just to summarize, for complex valued functions, we can treat those as concerning two real valued functions, each of which is a function of two real variables. The derivative of that function is well defined if and only if, as it turns out, these two functions satisfy the Cauchy-Riemann conditions. And if that is the case, then what we can do to form the first derivative of the function, we can form it as a partial derivative of one function with respect to one variable plus the object I multiplied by the partial derivative of one function with respect to the same variable. Or we can write it in this form here. So just to conclude, classical real-valued differential calculus, the object we reviewed in the third part of the module, we can extend that to the complex domain. But in order to do that, we have to introduce this technical precondition called the Cauchy-Riemann conditions, and these have to be satisfied. In effect, what these allow us to do is to reduce differentiation of complex valued functions to manipulating partial derivatives of real valued functions. Now, when we move on to look at integral calculus, this turns out to be much more challenging yet. And the reason why I'm going to look at integral calculus is because of a very important application this has in computer science and algorithm analysis. And that's a topic we're going to be looking at in the next lecture of the module.